Hi everybody, welcome back to Design 101. In this video, we're going to use what we learned in our last video about the design process and apply it to a real-life competition. In this instance, I chose the 2019 first competition, Deep Space. Hope you enjoy! So, as you know, the first stage of the whole design process begins at kickoff. In any competition, our team will gather waiting for the kickoff video, which I'll show you shortly, and an instructions manual detailing more of the specifics of the competition. So without any further ado, I'm going to show you the video of the Deep Space 2019 competition so that we can kick off our creative process. Here we go.
Welcome to the 2019 First Robotics Competition and this year's game, Destination Deep Space, presented by the Boeing Company. Two alliances of deep space travelers race to place hatch panels on their rockets and cargo ship, load valuable cargo for transport off the planet, and return to the safety of their habitat, all before the next sandstorm sweeps through. Each alliance has two rockets, one cargo ship, and a habitat. Hatch panels and cargo are available through the human player stations, and cargo is also available in the depots adjacent to the habitats. Robots start in their habitat and may be preloaded with one game piece. Alliances may also choose to preload some bays of their cargo ship with either hatch panels or cargo. During the first 15 seconds of each match, driver vision of the field will be blocked by a waning sandstorm. So robots must be controlled using either autonomous code or manually with a vision system on the robot. Alliances earn points for exiting the habitat, securing hatch panels, and any cargo that's properly stored. Cargo not secured spills from the cargo ship. As the sandstorm ends, driver vision returns, and alliances continue to earn points by loading their spacecraft. Alliances earn a rank point during qualifying matches for completing one rocket with hatch panels and cargo. Near the end of the match, robots return to the safety of their habitat for the upcoming launch and to earn more points. The alliance that earns the most points wins the match.
So that video right there, along with the rules and regulations that I talked about previously, is what really starts the whole brainstorming process for the design team. We use the tasks and the gameplay revealed in the video to start to talk about what we want to focus on, what we want our niche to be. So let's work through the video as we would in kickoff. The first opportunity for points that we are exposed to in the video is that we learn that we are able to manipulate hatch panels and cargo. We also learn that there's an autonomous period. However, for the 2019 competition, this autonomous period actually differentiated from previous autonomous periods that we talked about due to the fact that it was not fully simply coded, but it was you're actually able to use a camera to go through the sandstorm. So that was very interesting. We also learned that the hatch panels and cargo can be attained in two different ways. One is through the human player, and two is that they're previously placed in different spots around the game board. So we also got to keep that in mind when we're designing an intake. Do we want it to just be able to accomplish one, accomplish both? How complicated do we want to make it? Because an intake is going to be generally quite a bit more complicated if it's able to completely receive the cargo or the hatch panels itself without the aid of the human player. So we got to keep that in mind. We also learned that you can learn points for simply like exiting the habitat, which is also important to keep in mind when designing, because we want to like achieve the most points as possible, but we also have to keep in mind the simple points that we're able to achieve so that we can work on more simpler focuses throughout the game. We also learned that when you're storing cargo, there's different levels you can store it at. So that's another factor that we have to keep in mind when we're talking about the intake, because we're going to have to be able to manipulate it vertically as well. So a lot of challenges in this game. So in a regular season and at regular kickoff, we would look at all aspects of the game and decide which goals we want to make, like being able to perform in the autonomous period, and which goals that we are comfortable giving up, such as being able to use our intake for the hatch panels without the help of the human player. But for the purpose of this video, I'm going to focus on just one design process process of just one subsystem, simply just because we do not have the time to go over every single subsystem in the robot. So the one subsystem that I decided to focus on was the intake for the cargo or the rubber balls. So what does this design entail? Well, we can design, for example, a one-part intake that is able to intake the balls and expel them and manipulate them effectively. When thinking about this, though, we could consider the fact that having an intake that tries to do everything by itself might mean that we lose power and we wouldn't be able to reach the vertical rocket, so per se. Or we could design like a two-part intake and outtake that will take in the ball on one part of the robot and be able to expel it and manipulate it on the other part of the robot. This will give us power because we have separate motors, separate entities, that sort of thing. However, it could take up valuable space on the robot. So we need to plan the pros and cons of all these designs and visualize what they might look like. So that takes us to the next step, which is drawing or computer animated design. So after we've brainstormed and decided on our goals, which is solely just for the purpose of this video to design the subsystem that is an intake and an outtake for the cargo, it's time to start visually conceptualizing how we are going to achieve that. In our brainstorming, we came up with various ways that we might be able to intake and outtake the ball, but visualizing this brainstorming, which will help us discover what is the most efficient and the most attainable. So I've gone ahead and visualized a few different ideas for us to discuss. Unfortunately, I was only able to do this on paper. My computer's really old and slow, so it's still a respectable way to visualize our different ideas. So I'm just going to show you those in a few minutes. Okay, so here are the two intake designs that I made when we were keeping in mind that we had to manipulate this cargo right here, or this rubber ball as you'd like to call it. So the first design that I made here has a separate intake and outtake. You can see here our intake right here is powered by Omni wheels. It is just a rough sketch, keep that in mind. So this would be able to move up and down on here, taking the ball in from this plane, which would then put it into here, this like channel. And there's wheels on the sides, which when powered with motors, they're able to shoot up. Some of the notes that I made, the rough notes that give people that are looking at your design the ideas, is that it would be powered by pneumatics here, so that you're able to adjust the angle that the projectile is being shot out of, so that you can reach the top cargo holders and the bottom ones. I also wanted to show that these would both be powered by motors, both the wheels and the Omni wheels here at the bottom. And yeah, this obviously does not include the rest of the robot. It is simply an intake and outtake kind of design, but that's what I created for that. Moving on to the second one here, it's actually a one-part intake and outtake in one part of the design. There's not a separate place. It shows the two views here. So basically, the ball would be intaked down here with motors to possibly rotate this to be able to clasp onto the ball, and then this would move up here to be able to shoot it. Some of the notes that I have is that the pneumatics is what would power the intake to go from up here to down here and vice versa. That it might need more support because generally speaking this is going to have a lot of top weight and just pneumatics might not be able to power it. We've intake wheels on the side here that are able to intake the ball from when it's down here in this position, so the robot would be driving around and the ball is down here and we would drive up to it and take it using these wheels and then move it up here where we'd be able to shoot it up. So yeah, we're also able to rotate up here. Keep in mind also that, again, this only shows the intake part of the robot, nothing else like the motors, something that we might do for the hatch panels, nothing else, that just shows that. So yeah, these are my two intake designs. Okay, so out of these drawings, which one's the best? I'm joking. Well, none of them are objectively better than the rest of them. It is good to narrow it down as a design team in harmony with the other sub-teams, such as electrical, coding, programming, I don't know what you want to be called, Colin, and build, to decide which one is most attainable for the harmoniousness of the entire robot and is also effective for what we want to accomplish as a team. So when we narrow those down, we can finally decide what we want to start prototyping. So, prototyping. Well, I of course believe all my designs are amazing. Joking. I'm going to choose design number 2 to discuss a prototype for because that's actually the prototype that my team made when we were in the 2019 Deep Space competition. I was unable to create a prototype at home solely for this video, so that's why I'm choosing to display that one prototype. But don't think that you as a team can't choose more than one prototype. If you have two designs that you're discussing between, sometimes it is the prototype that says, hey, this is what we're able to do and this is what we're not able to do, and that is the deciding factor when it comes to prototypes. So as I said, you've seen this prototype before in my past video when I talked about the prototypes. However, this time I'm going to talk more about the drawing designs that I discussed previously and how they played out in this prototype, and also the prototype's main goal of seeing if we can accomplish what we designed in real life. So yeah. Okay, so it's time to discuss the prototype. Well, I know that you guys have seen this prototype before, as I talked about it a little bit in the last video when I was showing some examples of prototypes. I just wanted to go over it in the way where we're gonna see how we went from my drawings to this prototype in the way that we would in a competition. So I can't have both on the screen, unfortunately, but if you think back to the drawing that I just showed you, we were talking about, we're gonna look at how to make that into a prototype. So the first thing that we're going to want to do is look at what parts of the drawing kind of seem like we want to test out as a team. So when I look at it, I know for this prototype that I'm showing you the photo right here, my team only tested the claw intake part, the part that would hold the ball, as we were fairly certain with enough of extra support and stuff, the part that moves the intake up and down, like the steel rods that were connecting it to the robot, wouldn't require much prototyping. They were fully functional and that they would be good to go with the pneumatics and some extra support. So we really focused on prototyping the grabber part of the ball to see whether or not the wheels would function, whether or not it would be able to intake the ball, hold it as we moved it around, that sort of thing. So looking at this photo here that I showed you guys in the last one, you can see that we have it in the claw formation with the motors at the ends, which would have spun, and you'll see in the next photo, the intake wheels that would intake the ball. You can see that there's a metal bracket on the corner, so that obviously, at that point at least, was not free moving, so we were just testing whether or not the ball would be able to sit in there. You can also see that although at the bottom it's very faint, there's this rubber kind of band, and that would have been used, if I remember correctly, to open and close the kind of flaps and see whether or not we could put the ball in. I do have another photo here. One second. So yeah, this second photo here shows the prototype actually with the wheels attached. You can see that is not the same wooden base as the other one, so we obviously prototyped that. It functioned well, it held it well, and then the second prototype that we were making was more on the intake part of the wheels. So again, as you can see, it does not include the metal part that attaches to the robot, it's only the part that we want to prototype and refine and make better. So yeah, hope this helped you guys with prototyping. Okay, so now that we're happy with the prototype version of this subsystem and have smoothed out all the kinks that came along with the design, because I'm assure you that there will be many, it's time to start the final build of the robot. Well, there's not much design involved with build because everything's already been designed and it just needs to be built. I'm going to show you the final design again like I did in our last video and talk about how the prototype is the same, is different, how it differentiates, and how the final design ended up working. Okay, so here is the final build of the prototype, intake, subsystem, whatever you want to call it. You can see the intake on the right hand side there. It actually has the rubber ball in it, so this photo is a great indication of how well it worked in my opinion. But as you can see, it does incorporate pretty much everything from the start of the design. There's some extra things I just wanted to talk about. At the very bottom of the robot on the right hand side, you can see those two kind of random metal poles sticking up with pool noodle actually taped on them. Those are just so that when the intake goes downwards to pick up the ball, it doesn't crash into our bumpers. It also holds it at the right height to take the ball. So that's a little design innovation that we added in there. You can also see that on the top, in between like the claw part of the intake and the top of our metal structure on the left hand side of the robot, we have these two they're actually like medical tubing, they're stretchy. It's just extra support for our pneumatics that you see attached to the middle of the intake there. It just helped bring it up when our intake was down grabbing the ball. You can see that the claw part of it actually had the wheels and the motors like we were talking about, which allowed it to intake the ball when it was on the ground. It moved up and down fairly efficiently. It could shoot up and down. I know that at a later competition we added a sheet of like plexiplane glass on the very top of the ball to prevent it from shooting upwards. But other than that, this was a great design that was able to go all the way from the drawing stage through prototypes as an improvement and was able to work on the field. So yeah, I even have a video that I'm going to play for you shortly demonstrating how it worked, but overall amazing design.
Going over to the blue line, 6339, successfully placing one of their half panels on the cargo
Okay, well, that's the progression of the design process when applied to the first competition, Deep Space. I hope you enjoyed this video and that it helped you visualize what the design process is like applied to subsystems in a day-to-day competition, even though I wasn't able to do an entire robot, unfortunately. I'll see you next time.